In this video, we will talk about solving systems of ordinary differential equations. So far, we have looked at methods for numerically solving ordinary differential equations, or ODEs, with one variable y. Now, these are ODEs because there is only one dependent variable, t. So y depends on t only. And the ODEs we're solving are of the form dy by dt equals some function that depends on y of t, but may also depend on t explicitly. And we solve that equation given some initial data, y of t0 equals y0. Now, we only looked at first order ODEs so far. That is, those equations that involve the first derivative dy by dt, but not higher order derivatives such as d squared y by dt squared. That's the second derivative of y with respect to t, or higher order derivatives. They don't show up in this equation. The reason we did that was if we have higher order derivatives, we can always reduce those to a system of first order equations and then solve that system. But we have still not discussed how to actually solve systems of first order ODEs, so we will do that now. So we have a system of ODEs when we have multiple dependent variables. So if instead of just y, we have m variables, y1, y2, y3, and so on up to ym, then we have m unknowns and we have m equations describing those m unknowns, describing their evolution. And we can think of that as a vector y with an index I, and that's the evolution of that vector. And on the right hand side, we have functions that depend on all components of that vector. So y1 all the way up to ym, but they may also depend on t explicitly. So this is a system of first order ODEs. Again, it's first order because it only involves first order derivatives with respect to t. And t is still a scalar. So if t was not a scalar, we would have PDEs, partial differential equations, not ordinary differential equations. And if we had higher order derivatives with respect to t, then this would be a higher order system, not a first order system. Okay, so the first method we encountered when solving ODEs was the Euler method. That was based on approximating the slope at this first point, time ti, with the slope calculated by calculating y at t, or y at ti plus 1 minus yi divided by the interval, the time interval h. So if we set that slope equal to the slope at the first point and solve for y plus 1, we get this formula. We can also derive this formula using a first order Taylor expansion and keeping first order terms in h. And that expansion is an expansion around ti. Now we know we can do Taylor expansions for scalar functions, but we can also do Taylor expansions for vector valued functions. So that means the same numerical methods that work for scalar functions that we've seen so far are also going to work for vector valued functions or systems of ODEs that we want to use in this case. So an initial value problem will specify a value for each component of the vector y at time t0. So we have the first component at time t0, y1, that's equal to y1, 0, and the second component at time t0 equals y2 comma 0, and so on for all m components of the vector. Now, given this initial data for the vector y, we can evolve the ODEs that govern these components. So here's an example of two dependent variables. So we have two equations governing the evolution of two unknowns, y1 and y2. And of course, on the right hand side, we have functions f1 and f2, and each of those functions depends not only, so for example, f1 does not only depend on y1, but it also involves y2. So the same is true for f2. It depends on both y1 and y2. So this is a coupled system where each equation depends on all other equations. And again, we have two equations. We need initial data. We need two equations, or we need to define y1 and y2 at time t0. So we have a system of two equations for two unknowns. And to evolve that system, we need two initial conditions. So we can evolve that system using the Euler method, for example. So the Euler method will involve calculating the slope for each of those variables. So that's the first variable, or the first component of the vector y at time I plus 1, and that would be equal to yi plus h, the time interval h, times the slope f1, and then the same for the second component of the vector y. It will be the previous value plus the time interval times the slope. And here our notation is that y1 at I plus 1 is simply the estimate of y1 at time I plus 1, and yi is simply y at time ti, and so on. Now, note that this is simply an Euler step applied separately to each of the components of the vector y. Now, how do we implement this in C++? We can use the codes we have used before, but we need to organize the code a little differently when we have multiple equations. So previously we had a function such as f, so we defined double f, which depends on the arguments constant double y and constant double t, and so on. And that function returned the first derivative dy dt. And we also had a function such as a step Euler function that would take an Euler step using this function f and would return the estimate y at t plus h. So it would take one Euler step and calculate the function at the next step t plus h. Well, now we don't have one scalar function y here as input. Instead, we have a vector of y components. So that means we need to store the variables y1, y2, and so on up to ym in a vector of doubles of size m. And typically we do not want to copy these because this is less efficient, especially if y is a very large vector. So it's more efficient to pass the vectors of y values and first derivatives by reference, as we've shown before, as extra function arguments. And we will explain this in more detail in an exercise sheet. So let's look at the first exercise. So again, previously when we looked at solving a single ODE, we defined a function f of this form. So if we had an ODE dy by dt equals r times y, then that function f is just r times y. So this is what this function returns. So again, we have a constant double y as an argument here and a constant double t. And then we define the number r in here, and we return the product r times y. Now, if we want to do this for a system of ODEs, and let's suppose all ODEs are the same, so we have a vector valued ODE dy vector by dt equals r times y vector. Then we need to solve this system of ODEs. We need to change this function to fill in a vector of first derivatives. So instead of a constant double y here, we're going to have a constant vector double y. And then we also need to pass the derivative dy by dt. So we can have another vector double dy by dt. Now we notice two differences here. So first of all, we have a vector valued argument here, y, but there's also an extra argument showing up. And also there's this ampersand character here. So we use the ampersand because we want the vectors to be passed by reference. And this is done for efficiency. It is less efficient to copy each vector when we pass it to the function. The function would need to make a copy of that vector and then do operations on that copy. So that will waste memory and CPU resources. So by passing by reference, we've seen that this just passes the memory location where that variable is stored, and then the function reads it directly from memory without having to make a copy. So obviously that will be much more efficient. And again, y is passed as a constant because it's an argument and it's not going to be changed. Now, the slightly stranger thing in here is this vector double dy dt. That is the vector that will hold the first derivative, and we will calculate that here. So because we fill in the values inside the function here, that means this vector is not constant. We're going to change its values inside the function. Also, the function is now a void because it's not returning a value. Right now, we're not using return to return some value. Instead, we use the function to directly modify the components of the vector and fill in the input vector components, basically, instead of returning the first derivative. And we will call that function and use a loop here. Now, inside this function, I'm only updating the first component, but we're obviously going to need a for loop to update all components. So here we can modify our main function. So first we calculate the time steps, the time step h, the number of points, the initial time t0, the final time t, and so on. And after we do that, we construct a vector y with our initial data, another vector dy dt of size m, and here we don't specify the components of the vector yet. We're going to fill in the components using that function. And then we have a for loop that goes through different time steps. So the index I goes from 0 up to n, where n is the number of time steps. And then inside that loop, for each time step, we call the function f, x vector. That function will update dy by dt. And then with the for loop, we update to the next step. So we do an Euler step based on this dy by dt. So yj becomes yj plus h times the slope, where the slope was calculated using this function. Okay, so now let's consider a slightly more interesting model. For example, let's look at the SIR infectious disease model. So that model is the spread of an infectious disease. The population is divided into categories according to their infection status. And we assume that the model describes a total population that is large enough that we can treat the numbers in each state as continuous quantities. Now, the SIR model involves three quantities, S, I, and R. S is for susceptible, I is for infected, and R is for recovered and presumably immune to reinfection. The total population, N, is S plus I plus R. If we ignore births and deaths, then the differential equations that govern this model are ds by dt equals minus vita si, di by dt equals vita si minus alpha I, and dr by dt equals alpha I, where alpha and vita are constants, and t is time in this case. And in particular, the constant vita is the rate at which an infected person can infect others, and alpha is the rate at which people recover from infection. Now, this model does not have an explicit formula as a solution, so it needs to be solved by numerical methods. And the reason it's not easy to find an exact solution is that this is a non-linear system of equations. So the product Si is quadratic in the variables. It depends on the product S times I. Okay, so we can put this system in the notation we used previously. So for example, we could take y1, the first component of the vector, to be S, the second component equal to I, and the third component equal to R. And then the function f1 of the vector y would be equal to minus vita si, or minus vita y1 times y2. And similarly for f2, that is equal to vita si, or vita y1 y2 minus alpha times I, or alpha y2. And finally f3 is alpha times I, so that's alpha times y2. Now we will solve this system numerically as part of the exercises, but let's look at the solution, how it looks like. So the number of infected people initially increases, so almost exponentially at first, then it levels off later. The number remaining susceptible, at first it's 100%, then it falls off as more people get infected and become immune or develop antibodies, and then that decreases substantially as time goes by. And when S and I approach some asymptotic constant value, so some people will become infected and recover. Some people, like the blue line, will be the people that will not get infected and will remain susceptible. When these approach a constant, we have basically reached herd immunity, and the number of infected people, currently infected people, is the red line, I, and we see that this number will start to fall off after roughly when the blue and green lines cross. And eventually, once we reach herd immunity, the number of infected people drops off dramatically. Now, there are some possible checks that we can do on our numerical solutions to see if they are accurate and if they're valid. So first of all, the sum of the three states n equals us plus I plus r, that should be constant. So that's the total number of people, and because this model ignores births and deaths, the total number of people should remain constant. We can use that to check the accuracy of our code, or if it changes a lot, then there must be a bug in our code, for example. Also, the model has a threshold quantity given by R naught equals beta n divided by alpha. And it's possible to show that the infection infects a substantial proportion of the population if and only if R naught is greater than 1. That means that the infection starts spreading exponentially, at least initially, and if R naught is lower than 1, then the infection is getting decreased exponentially. Another check is to look at this constant, asymptotically constant ratio of S divided by N. That's the proportion of the people that remain susceptible. So that's the limit at late times of S divided by N. That proportion, let's call it P. Asymptotically, that satisfies log P equals R0 times P minus 1. And there's a similar relation for the number of infected people. So we can check if this identity is satisfied at late times. And obviously we don't need to remember any of this, we can just look it up. But our main goal here is to code this up in C++ as part of the exercises, and then use these relations to see how accurate our code is. And that's it for this video. Thank you for watching.